Welcome back to class 6. All right, so this is, we're dealing with strain gauges, and here's an example from Philpot's 3rd edition. And we have this rosette, and we're able to measure the strains. And we want to find out what the stresses are from these strains. This is a very practical implementation, a real-world thing, because we can't really measure stress. We can measure strain, so that's our motivation in doing a problem like this, right? And I have actually done this in the real world, and it's a useful thing to be able to do, to be able to find. So the angles, and by the way, they're not using 1s and 2s and 3s, they're using A's, B's, and C's, but with the equations that we gathered from the last class, the equations that we'll use, by the way, this is not in our textbook, by the way, but the equations that we'll use, let's see, I'll put them back up here. These are the basic equations that we're going to use for these interrelationships in the generic strain transformation type of thing. I think there's another way to do this. I haven't really looked at it in a while, so I don't want to like speak knowledgeably about it, but you can do something similar to this with a something that's analogous to Moore's circle, by the way. But in this case right here, we're going to say that we're going to have theta A. We're going to say that that one is going to be 315 degrees, and theta B is going to be 0, and theta C is going to be 45 degrees, right? So that's the things that we're going to use. We're going to use the total angle. By the way, that is the same thing as saying E is equal to 10 MPSI, right? So this is aluminum. Steel is close to 30 in its Young's modulus, so that's a good thing to keep our track of. And you'll see that this is the Poisson's ratio of 0.33. So this thing's on the surface of an aluminum component, and the strain rosette picks up these things. And they use micro strain. So all that really means is that's e to the minus 6, right? That we're placing on there, and that the strain just means, that epsilon just means inches per inches, right? Or millimeters per millimeters. We're in US units, so there'll be inches per inches, but it doesn't matter as long as we know right here. So I'm going to my first equation, I'm going to use, I'm going to substitute in, I'm not going to rewrite the equations out because that would take too long or add to the length of the thing. So I'm basically rewriting out that equation right here and populating it, and instead of 1, I'm going to use A, right? So I write out, and I'm going to put in the number, the value right here. So we're going to say that 440, and we're going to wait until we get to the end. Let's leave off all the e's to the minus 6's to the very end of the thing until we get an answer. We're going to say it's going to be equal to epsilon x, we want to know, cosine squared of, whoop, I did it, 315, or negative 45, right? Plus epsilon, whoop, I switched between my epsilon types. And I did it on my sheet over here too. There's 2 different ways to write epsilon. I'm writing this one. Sine squared of 315. And I didn't leave a lot of room for this. Gamma xy, sine of 315, cosine of 315. And we could actually, let's see, 315 cosine squared is, this is 0.5. And this right here, I anticipate that to be 0.5, right? 315 sine, and then square it. And it was, where did you go square? I lost it. I lost it. No. There you go. You see, this would be a negative. Sine of that would be negative, but it's squared, so it's still right there. But this guy right here, now he is going to be negative 0.5 times negative 0.707 times 0.707. So he's going to be negative 0.5, right? But we have three unknowns. These are three unknowns. Let's go to B now. B has 550. So we'll go 550 is equal to epsilon x cosine squared of 0 plus epsilon y sine squared of 0 plus gamma xy sine 0 cosine 0. Well, of course, this is going to be 1. That's going to be 0. And this is going to be 0. Right? So we could just say that epsilon x is equal to 550, and we'll just call them microstrains for right now, and like that. And now maybe I'll switch over to the other epsilon. Okay, so we know this one. So now we have two unknowns up in this guy right here. So we're going to use the other equation right here. So we have 870 is equal to epsilon x cosine squared of 45 plus epsilon y sine squared of 45, and we know we're going to get the same thing before, right? That's just going to be 0.5, and that's just going to be 0.5. But here we have the gamma xy and sine of 45, cosine of 45, and this one right here is going to be positive 0.5 right there, right? So there's our two equations and two unknowns, right? We have, because we know epsilon x, so we could put them into both of those equations, and so we could solve this simultaneously, and if we do that, I won't bother with that, but we could. We get 760 microstrains, and then our gamma xy from that gets 430 micro. And by the way, this one is actually microradians. So just to be aware of that. So now we have to. That's right there. We just did the strain transformation, and we're able to get strains in the axes that we actually care about, in the directions we care about. And then we want a simultaneous, no, we don't have to do that. Now we could just say sigma x, and I'll write down what that equation was that we had for biaxial stress condition. Right here, mu, nu, not mu. So if we stick that in there, and we have 10e to the 6 divided by 1 minus 0.33 squared. And this right here is going to be 550 e to the minus 6 plus 0.33 times 760 e to the minus 6, and I ran out of room. My margins. I get a stress of, and then I'll write it down. 8,986 psi, or as we like to just write it out, 8.99 ksi, and it's positive, and that the positive and negatives do matter here because we can't have compression onto the thing. And similarly, I got lazy apparently. Similarly, sigma y is going to be 10.6 ksi in tension. And then when we go to find the tau, let's first get the modulus of rigidity, because we were given elastic modulus and Poisson's ratio. So let's take that, and E divided by 2, 1 plus nu, or 10E6 divided by 2 and 1 plus 0.33. It becomes 3.759 E6. These are PSI, right? So tau xy is equal to g gamma xy and 3.759 E6 times our 430 microradians E minus 6. So tau xy is equal to 1,617, or here 1.62 KSI. Right, so, and if I wasn't so lazy, I would have written that out again right there. But there's an application, and we can. I'm going to do some more examples, and we'll see that from those examples that we have actually. There's actually real stuff in the real world that would actually matter to us that we would want to find out from this. So there you go. Example 1. We'll do, I think, 2 more examples, maybe just 1 more example. I don't know. We'll see how I feel.